Alright, let's go. Number 10. The Great Attractor. In the mid-1980s, a collaboration of 7 astronomers, Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lyndon Bell, Roberto Terlevich, and Gary Wegner, set out to do something almost dull. They wanted to measure distances to about 400 nearby elliptical galaxies. The goal was calibration. Better distances would mean a better map of how galaxies drift against the expanding cosmic background. Standard cosmology predicts that on scales of a few hundred million light-years, galactic motion should be almost entirely the smooth flow of universal expansion. Small deviations, called peculiar velocities, might reach 100 or 200 kilometers per second, driven by nearby clumps of matter. Nothing more. The universe at that scale is supposed to be quiet. Their data was not quiet. Every galaxy in their survey, including the Milky Way, the Local Group, the Virgo Cluster, everything within about 200 million light-years, was drifting coherently in one direction, toward a point behind the plane of our own galaxy, in the constellation Centaurus, at roughly 600 kilometers per second. The results appeared in 1988 in the Astrophysical Journal. The group became known as the Seven Samurai. The pole was named the Great Attractor. It sits about 250 million light-years away, hidden behind the zone of avoidance, the band of dust and stars in the Milky Way's own disk that blocks nearly a fifth of the sky. Every explanation fell short. The Norma cluster was proposed as the source, too small. The Shapley supercluster, 600 million light-years further out, was invoked. The flow continues past even that. In 2016, René Cron-Cordoveg's team at the University of Cape Town uncovered the Vela supercluster behind another obscured patch of sky. More mass, still not enough. The pull continues. No known structure fully accounts for it. Right now, as you read this, you are moving towards something at more than 1,000,000 miles an hour, and no one on this planet can tell you what it is. How much more is buried behind the disk we cannot see through? But being pulled towards something hidden is not the strangest thing about where we live. Number 9. The KBC Void. In 2013, 3 astronomers at the University of Hawaii, Ryan Keenan, Amy Barger, and Lennox Cowie, were doing near-infrared galaxy counts, not a glamorous project. They were compiling numbers of galaxies per unit volume out to about 2 billion light-years, trying to pin down how the local universe compares to the cosmic mean. The prediction from standard MULCDM cosmology is straightforward. On scales larger than roughly 300 million light-years, the density of galaxies should be uniform, within a few percent. That's the cosmological principle in practice. It is the foundation on which nearly every cosmic distance measurement rests. Their counts didn't cooperate. They found that the Milky Way sits inside a region of space, roughly 2 billion light-years across, in which the galaxy density is about 20% below the cosmic average. Their paper, published in the Astrophysical Journal in 2013, described what has since been called the KBC Void. Keenan, Barger, Cowie. It is the largest known underdensity in the observable universe. The failure parade is short and painful. Selection effects were ruled out by cross-checking with independent surveys. Dust extinction was corrected for. In 2020, Moritz Haselbauer, Indranil Banik, and Pavel Krupa published in monthly notices of the Royal Astronomical Society that a void of this size and depth is inconsistent with Eildaldaum predictions at more than 6 sigma. Some researchers, including the Krupa group, argue the KBC void partly explains the Hubble tension, that the reason nearby distance measurements yield a faster expansion rate than the cosmic microwave background is that we're measuring from inside a bubble that has an unsettling consequence. Every observation you have ever heard quoted about the age or size of the cosmos was made from Earth, from inside the void, if the void is real. What if the universe you have been shown is a local view, misread as a global one? The place we are pulled from turns out to be almost as strange as where we are going. Number 8. The Cosmic Web Filaments. For years, a team led by Hideki Umehata at Ariken in Japan had been studying protoclusters, enormous clumps of forming galaxies in the early universe. The goal was to understand how gas flows into these regions and fuels their growth. Standard theory says gas should follow thin, tangled threads of dark matter, the cosmic web, accreting quietly onto galaxies. Simulations, particularly those from the Illustrist NG and Eagle projects, predict filaments a few megaparsecs long, dominated by cold hydrogen. The gas should be diffuse, difficult to image, detectable only through indirect signatures. The picture, though hard to see, is supposed to be settled. The image they captured was not. In October 2019, Umehata and colleagues published in Science direct optical images of Lyman alpha emission from the cosmic web feeding the SSA-22 protocluster, roughly 12 billion light-years away. The filaments glowed, visibly, across more than 3 megaparsecs of sky, longer, brighter, and more coherent than the simulations had predicted, every explanation strained. Boosted ultraviolet background could brighten filaments, but not enough. Increased gas fractions violate independent constraints from the Lyman alpha forest. Some researchers argue for embedded, undetected populations of faint AGN illuminating the gas from within, but the ionization signatures don't quite match. Follow-up work by the MUSE team at ESO has since found similar overextended filaments at other redshifts. The problem is not going away. The cosmic web is not a decoration. It is the scaffolding on which every galaxy, including ours, hangs. If the simulations are getting its geometry wrong at this scale, then the story of how the Milky Way was built, the story of how the atoms in your bones were delivered to the place they now sit, has a piece missing. What else are the simulations quietly getting wrong? The structures we can see are giving us their own problems. Number 7. The South Pole Wall. Daniel Pomerade at Paris-Saclay, along with R. Brent Tully at the University of Hawaii, and Hélène Courtois at the University of Lyon, had spent years extending the Cosmic Flows Survey, a catalog of galaxy distances and peculiar velocities. They were not hunting for a structure. They were reconstructing the local density field to make better sense of the flows we already knew. The prevailing view was that the largest coherent structures in the local universe, walls and superclusters, top out around 300 or 400 megaparsecs. Anything much larger begins to look uncomfortably close to violating the cosmological principle. The map, we thought, was mostly drawn. Their reconstruction disagreed. In July 2020, Pomerade, Tully, Courtois, and Yehuda Hoffman published in the Astrophysical Journal the discovery of the South Pole Wall, a filamentary structure of galaxies extending roughly 1.4 billion light-years across the southern sky. It had been hiding behind the Milky Way's southern plane, obscured by the same kind of foreground dust that concealed the Great Attractor. Nothing about it fits neatly. It wasn't seen in the earlier 2 mass redshift survey because it sits partly in the zone of avoidance. It wasn't predicted in prior density reconstructions because the data simply wasn't there. Cosmic Flows 3 caught it only because the peculiar velocity field encodes mass we cannot see directly. Later attempts to fit it into standard structure formation simulations found that walls of this size are rare, not impossible, but sitting at the tail of the distribution. The uncomfortable part is this. The South Pole Wall was found in 2020, in a region of sky humans have been photographing for centuries, right next door, cosmically speaking, and nobody knew it was there. If a structure this large, this close, escaped detection until 5 years ago, how much of the map is still blank? Bigger structures, closer to home, keep getting bigger. Number 6. The Large Quasar Group. Roger Close at the University of Central Lancashire had been maintaining a catalogue of quasar groupings for over 2 decades. His work was cataloging the unglamorous business of clustering distant, ancient galactic cores into associations. Nobody expected him to challenge the foundations of cosmology. The theoretical ceiling on how large a coherent structure can be, given Cell-Tomé-Slels, had been calculated in 2010 by Jaswant Yadav, Jayanti Bagla, and Nishikanta Kandai at Punjab University. Their result, published in monthly notices of the Royal Astronomical Society, put the upper limit at about 370 megaparsecs, roughly 1.2 billion light-years. Anything larger would be, in their words, at odds with the cosmological principle. Close broke it. In January 2013, Close, along with Harris, Raghunathan, Camposano, Sutching, and Graham, published in monthly notices the huge LQG, the Huge Large Quasar Group, a cluster of 73 quasars stretching across roughly 4 billion light-years, more than 3 times the Yadav limit. And they weren't alone. A year later, Istan Horvath, John Hakila, and Zsolt Bagoli, using gamma-ray burst positions, mapped what they called the Hercules Corona Borealis Great Wall, a structure about 10 billion light-years across. The counterattacks came fast. Seshadri Nadathur at the University of Portsmouth published a 2013 rebuttal, arguing the huge LQG could be a statistical artifact of the Friends of Friends algorithm, that random point distributions, run through the same clustering method, can produce apparent structures of similar scale. The debate has not resolved. Some cosmologists treat the LQGs as real, others treat them as ghosts. But if they are real, then the universe on its largest scales is not smooth, it is lumpy. And the entire framework we use to calculate its age, its expansion rate, and its ultimate fate assumes it isn't. What counts as a structure, and who gets to decide? The problem isn't only that structures are too large, it's that our rulers are misbehaving. Number 5. The Baryon acoustic oscillation tensions. The BAO story begins in the early universe, when hot plasma rang like a bell. Sound waves rippling through the pre-recombination cosmos left an imprint, a characteristic scale, about 147 megaparsecs, at which galaxies today are slightly more likely to be found. This scale can be measured in the cosmic microwave background at redshift 1100 and again in galaxy surveys at low redshift. If cosmology is self-consistent, both measurements should agree. For 20 years they mostly did. The Sloan Digital Sky Survey team, led by figures including Daniel Eisenstein at Harvard and later the EBOS collaboration, matched the CMB prediction within errors. The standard model held. Then came DZ. In April 2024, the Dark Energy Spectroscopic Instrument collaboration released its first-year cosmology results, 6 million galaxy and quasar spectra. The paper, led by hundreds of authors, showed a preference at roughly 2 to 3 sigma for a time-varying dark energy equation of state, W0 WACDM, over the flat NEL-CDM model. When combined with Type 1a supernova data, the tension climbed. In 2025 follow-up releases, the tension persisted, with independent analyses by groups including Eleonora Di Valentino at Sheffield and Adam Rees at Johns Hopkins weighing in. Every proposed escape has cost something. Systematic errors, sky masks, fiber allocation, redshift precision have been chewed on and mostly survived. Modified early universe physics resolves the Hubble tension but sharpens others. New dark energy models can accommodate the data, but require extra parameters nobody wants to add. The measuring stick physicists have used for 2 decades to gauge the expansion of the universe appears, in the newest data, to be giving different answers at different distances. If early and late measurements of the same cosmos disagree, which universe is the real one? The rulers bend. The mirrors line up in ways they should not. Number 4. The axis of evil. In the early 2000s, the WMAP satellite had just delivered the most detailed all-sky map of the cosmic microwave background ever made. Cosmologists were decomposing it into spherical harmonics, the natural language for spherical data, expecting the largest angular modes, the quadrupole and octupole, to be statistically independent and randomly oriented. The universe, on the largest scales, has no preferred direction. That is a bedrock assumption. Kate Land and João Magaja, at Imperial College London, decided to test the assumption directly. In 2005, they published in Physical Review Letters an analysis of the quadrupole and octupole orientations in WMAP data. The 2 axes lined up, not just close. Aligned to within a few degrees, with a chance probability, under Land and Magaja's analysis, of roughly 1 in 200. They named it, half in jest, the axis of evil. The alignment also sits suspiciously close to the plane of the ecliptic, the plane of our own solar system. As if the largest features in the universe are oriented with respect to Earth's orbit around the Sun. Everyone tried to kill it. Improved foreground subtraction, the removal of galactic microwave emission, reduced the significance but did not eliminate it. Planck, the more sensitive successor mission, confirmed the alignment in 2013 and again in 2018, though at reduced statistical weight. Some argued a posteriori statistics. You can always find some alignment if you look for enough of them. Others argued unknown foregrounds. Nothing has fully explained it. The straightforward reading is that either the universe on its largest scales knows about Earth's orbital plane, which is absurd, or our theory of what the CMB should look like on its largest scales is wrong, which is only slightly less absurd. What kind of coincidence is that? Alignment is one issue. Whether the universe becomes smooth at all is another. Number 3. The homogeneity scale. The question sounds childish until you try to answer it. At what distance does the universe start looking the same in every direction? For decades, cosmologists have assumed the answer is around 300 million light-years, beyond which any patch of the cosmos looks statistically like any other. It is not just an assumption of convenience, it is what makes del CDM tractable. In 2012, Morag Scrimger and colleagues, using the Wigglesy Dark Energy Survey, published in Monthly Notices of the Royal Astronomical Society, a measurement placing the transition to homogeneity at about 70 megaparsecs per h, well within the standard expectation. The community, on the whole, moved on. Others did not. Francesco Silos Labini, at the Enrico Fermi Center in Rome, alongside Luciano Pietranero and collaborators, has argued in a series of papers stretching back to 2009 in Europhysics Letters, and continuing through the 2020s that galaxy distributions show fractal-like behavior out to 300 megaparsecs per h and beyond. Their reanalyses of Sloan data suggest the universe never quite becomes as smooth as Leppeus CDM assumes. The debate has resisted resolution. Different definitions of homogeneity, number counts versus correlation functions versus fractal dimensions, give different answers. Sample geometry matters. Selection effects matter. Nobody has produced the clean, undisputed measurement that would end the argument. If Silos Labini is right, the smooth cosmos on which the standard model is built is a mathematical convenience, not a physical fact. Every calculation of the universe's age, every estimate of its expansion, every model of dark energy, assumes a smoothness that may not exist at the scales we invoke it. What if the universe never fully smooths, and we've been dividing by an imaginary constant this whole time? If smoothness is uncertain, so is our sense of what we're moving with, or against. Number 2. The dark flow. In 2008, Alexander Kashlinsky at NASA Goddard had been working with an unusual tool, the kinematic Sunyaev-Zeldovich effect, a tiny distortion of the cosmic microwave background caused by galaxy clusters moving relative to the CMB rest frame. Combined with an X-ray selected cluster catalog, the KSZ effect can, in principle, measure bulk flows across enormous distances. The prediction from SIBDM is that bulk motion on scales beyond about 200 megaparsecs should die out. There should be no coherent drift of galaxy clusters across cosmological distances. The universe has no preferred flow at those scales. Kashlinsky claimed to have found one. His team, Kashlinsky, Fernando Atrio Barandella, Dela Kuchevsky, and Harold Ebeling, published in Astrophysical Journal Letters in 2008 and 2010 a coherent motion of galaxy clusters of roughly 700 to 1,000 kilometers per second, extending out to 1 billion light-years, directed toward a point in the southern sky near Centaurus and Vela. They called it the dark flow. If real, it could not be caused by any structure within the observable universe. The refutations came in force. The Planck collaboration, using their own KSZ analysis in 2013, found no significant bulk flow at those scales. Follow-ups by Stephen Osborne and others argued Kashlinsky's methodology overestimated the signal. Kashlinsky pushed back, arguing Planck's analysis was less sensitive than his, and published continued defenses into the late 2010s. The dispute has never been cleanly settled. If the dark flow is real, then something outside the observable universe, something we cannot in principle see, is pulling matter within it. Every atom in your body would be drifting toward a place light cannot reach us from. Can we ever test what lies beyond? Every anomaly on this list has one shared enemy. Number 1. The cosmological principle itself. The cosmological principle is not a discovery. It is an assumption. Einstein invoked it in 1917 to make general relativity solvable at cosmic scales. Edward Milne formalized it in 1935. Every model of the universe you have ever encountered, the Big Bang, inflation, dark energy, Zilla-Day M, takes it as a starting point. The universe is isotropic, the same in all directions, and homogeneous, the same in all places, at sufficiently large scales. The prediction it makes is deceptively simple. Beyond a few 100 million light-years, no direction is special, no place is special, and any observer anywhere sees, on average, the same cosmos. Every entry on this list has taken a small bite from it. The Great Attractor and the South Pole Wall show us structures we didn't know existed. The KBC Void places us inside an underdensity that shouldn't exist. The huge LQG and the Hercules Corona Borealis Great Wall stretch beyond the theoretical maximum. The axis of evil suggests a preferred direction. The homogeneity scale is disputed at its foundations. The BAO tension and the dark flow, if real, break the picture from opposite ends. In 2023, Pankaj Chen Pavan Kumar Alluri and colleagues published a review in Classical and Quantum Gravity cataloging over 24 observational tensions with the cosmological principle. Each one alone is survivable. Together they are harder to dismiss. Every rescue attempt costs something else. Modified gravity fixes one anomaly and breaks two. Void models resolve the Hubble tension and worsen the BAO tension. Bianchi cosmologies with a preferred axis explain the CMB alignment and require rewriting every cosmological distance in the literature. There is no clean fix. If the cosmological principle is wrong, even partially, then every number you have ever been told about the universe, the age of it, the size of it, the fate of it, is a number calculated from the wrong map. What if the universe was never uniform, and we've been reading a story that was never there? The universe is not confused. We are. Every anomaly on this list sits not at the fringes of physics, but at the center of our most tested, most trusted theories, the ones we use to measure everything else. When the map disagrees with the territory, cosmologists have historically bet on the map. This time the territory keeps sending back the same signal from a dozen independent directions at once. What we call the standard model of cosmology may turn out to be the standard model of the cosmos we imagined, not the one we actually inhabit. If you want to see more videos like this, click the video on screen now.